Hi, in this video we're going to download and install the extended tight binding semi-empirical program XTB from the Grimme group. This is a very powerful molecular simulation software that uses semi-empirical methods as well as force field methods to do different types of calculations such as geometry optimizations and molecular dynamic simulations on very large molecular systems. So I googled for XTB Grimme and I found here the homepage of the Grimme group in the University of Bonn. I'm in the software tab, and here I'm going to press the link to the binaries in a new tab, and this will send me to a GitHub repository where I can download the binaries for the program. There are different files. I'm going to download XTB 671 version for Linux, and after that I'm going to move it to the computational cluster that I use for my calculations. Now I have copied the tar file to my home folder in the cluster, and I'm going to untar it. I'm using PowerShell, so I will connect to the cluster. I'm already at the folder, so I will write tar-xf and the file with the extension. So the program is unpacked, and I'm going to run a test calculation to see if it works, and then I'm going to explain a little bit. Here are the coordinates. This calculation contains 664 atoms, and below the coordinates we have some options for running the molecular dynamics, such as the temperature, the total simulation time 50 picoseconds, and the step size 2 femtoseconds. We also have some other options, like for example the shake option. Shake equals 1 means that we will allow the bond lengths to change for all atoms except those bonds containing hydrogen. The shell file is very important, so here are some general options that I use for running the calculations on the QA system in the cluster, and there are some specific options for XTB, like exporting the binaries to the path and setting the memory, max memory per core, and the number of cores on a certain node. I'm calling the binary file XTB, and I'm putting the input file name, the output file name, and some other options. So --OMD is optimize, then do a molecular dynamics, and this I'm setting the charge. I will set up the charge as +1, and I'm basically saying that there will be 1 unpaired electron. So this would be unrestricted Hartree-Fock. So if I copy this to the cluster, the calculation should start. So I just copied this into a folder. I always use a separate folder for each calculation. And if I go there, I will go to the appropriate folder, and let's hope it works. Okay, it tells me it is configuring. That means it's still, the calculation has not started, but while we wait, I will show you some previous calculation that I already did. Okay, so basically this is a calculation of a cobalt corroll that I work with, or a similar one that the ones I work with. Basically in a droplet of acetonitrous, I had pre-optimized this structure, so I'm not starting from a totally new structure, but this has been a molecular dynamics run. So I will just change the aspect of the corroll so that it can be better seen. If I go to display mixed, I can choose a slightly different visualization. So if I move, we can see the molecular dynamics. So this is basically a semi-empirical quantum calculation. So it allows chemical reactions to happen. That is much more powerful than a classical force field. And it still allows pretty large systems to be simulated. Of course, it takes some time. But these molecular dynamic simulations of around 660 atoms involve 50 picosecond runs, which is not a small number, and they lasted a couple of days on 16 cores. So this is really, really fast. And I think that I can easily get to 3,000 atoms, but of course that will take more memory, so the calculations will have to be done on not so many cores, and because the system is larger, that will take several days. But still, those are very large systems that allow a lot of chemistry to be observed. So we see here a little bit of flying acetonitrile that happens when you simulate a solvent and you don't put some kind of box with some boundary conditions, or you put some pressure on the box. So basically it's evaporation of the solvent. But at this point, I'm not really interested in that. I'm just learning how to use XTB. If I look at the energy data summary, show energy graph from multiple XYZ file, we can see how the energy goes from a previous initial optimized geometry, starts the molecular dynamics, and over 1000 steps here, 50 picoseconds, we get like a thermalization of the system. So my job is still under configuration. So this means that basically all nodes are busy. So I cannot start the calculation right now. It will probably start in a few hours, but I will have to update you later on if this calculation worked. The only difference between the calculation I just showed is that I was doing that in a previous version of XTB. I was using version 6.4.0, and now I have shown you how to install the latest version, 6.7.1. But everything should be the same, and hopefully everything will work with no need for extra configuration. So this is all for this video. I hope that you have found it useful. Happy 2025, and let's hope we will see each other around. Thank you.